All right, let's dive right in. Today, we're looking at something really fascinating. A source that takes a physics thought experiment that's over 100 years old and completely re-examines it, but not on a chalkboard. No, they're using modern 3D visualization tools, and it's a pretty bold challenge to a very, very famous idea.
So this is the big question right at the heart of the material we're looking at today. The author is basically suggesting that a foundational concept in modern physics, one that we have relied on for over a century, might just be built on a shaky foundation, on a faulty premise from the very beginning.
But before we even get to the challenge, you have to understand the sheer scale of the ideas being questioned. The source itself actually kicks things off by acknowledging the absolutely immense and foundational contributions of Albert Einstein.
Our source zeroes in on three of Einstein's towering achievements. First up, his work on Brownian motion, which was crucial in proving that atoms were real, basically setting the stage for all of modern physics. Second, his explanation of the photoelectric effect, which became a cornerstone of quantum mechanics. And third, and this is a more controversial point the source makes, is that his work indirectly paved the way for the atomic bomb.
And this really captures the scope of his influence, doesn't it? His ideas give us a framework for understanding our universe at literally every scale, from the super strange, probabilistic world of a single atom all the way up to the cosmic dance of entire galaxies. Okay, so let's get to the core of the issue. We're going to break down that famous thought experiment that sits right at the heart of special relativity. And yeah, it involves a train, a flash of light, and two very, very different points of view.
The setup is famously simple. So imagine a single train car, and it's just cruising along at a constant speed. And then, boom, a light bulb flashes at the dead center of the car. The question that changes everything is, what happens next, depending on where you're watching from?
Now, if you're a passenger on the train, the answer seems like a no-brainer. You're moving right along with the light source. Since it flashed from the exact middle, the light has the same distance to travel to the front wall and the back wall. So to you, the light hits both ends at the exact same time. Simple enough, right?
But here's the twist. For someone standing on the platform watching that train zoom by, the picture is completely different. In the time it takes for the light to travel, the back wall of the train has actually moved forward to meet the light ray. Meanwhile, the front wall has moved away from its light ray. So for the person on the platform, the light hits the back wall before it hits the front wall. And this leads to one of the most mind-bending, absolutely wild conclusions of Einstein's theory, the relativity of simultaneity. The very idea of two things happening at the same time is not absolute. It completely depends on your frame of reference.
This concept is a pillar of modern physics. It's fundamental. But what if, as our source material suggests, this is the exact spot where a massive error was made over a century ago?
And the source does not pull any punches here. The author makes a pretty pointed claim, as you can see in this quote. They argue that for over 100 years, the physics community just accepted this thought experiment, not because the logic was unassailable, but because of the authority of the person who came up with it.
So, as a replacement for relativity, the source proposes a completely different way of looking at reality. This is what they call the Zionad-Chat model. It's a geometric alternative that basically redraws the entire relationship between us, the observer, the physical events, and the information we get from them. So, what does this new worldview actually look like? Let's break down its key components. At its heart, it's a really visual, geometric way of looking at the world.
The model makes a really critical distinction. As you can see, you have this flat plane of physical reality. That's where the train is actually moving. But, and this is crucial, the observer doesn't see that directly. Instead, they perceive everything through what the model calls a spherical window, which is kind of like a perceptual filter centered on themselves.
Okay, so how does information get from that physical reality to the observer's window? Well, the model introduces this concept of postal light rays. You can think of these as little information packets that travel in a straight line from the event, like light hitting the train walls, right to the observer's eye at the center of that sphere.
And here is the absolute crucial difference. In relativity, the train is basically an abstract reference frame. But in this new model, the train is a concrete, physical object that's moving through an electromagnetic field. Now that might sound like a small change, but it fundamentally alters all the calculations.
And this leads to a core prediction of the model, something it calls time asymmetry. The idea is that because the train is a physical thing moving through a field, light that's traveling in the direction of motion actually takes longer to cover the length of the train than light traveling against the direction of motion.
Now, this is where the whole argument shifts from these abstract diagrams to a practical, testable model. The source uses 3D visualization software not just to draw their ideas, but to build a tool that actually calculates the consequences of this new geometry.
And this shows that jump from theory to practice perfectly. On the left, you've got the conceptual diagram we've been talking about, and then on the right, you can see that exact geometry brought to life inside a 3D software program, which lets the model be tested visually.
So this isn't just a fancy drawing program. It's a dynamic calculator. It's doing the core math of the entire model, calculating precisely where those postal light rays hit the observer's spherical window. This is what allows the author to actually make predictions that can be tested.
What makes this so powerful is that it's interactive. Anyone can go into the side panel and change the variables, the size of the sphere, where the light ray comes from, the angle, and instantly see how that affects the geometry of perception, at least according to this model's rules.
And this is key. The tool doesn't just work inside its own little bubble. It can also generate the classic Minkowski space-time diagrams that are used in conventional physics. This means you can do a direct, visual, side-by-side comparison between the predictions of this new model and the traditional one.
And this all brings us to a final, pretty provocative thought. Whether this specific geometric model is ultimately right or wrong is almost beside the point. The bigger story here is how these powerful, accessible tools are letting anyone, not just people in university labs, not just question, but rigorously model and visualize alternatives to our most established scientific theories. The thought experiment has well and truly entered a new era.